Welcome back to the second introductory lecture on proofs. In this sixth and last segment, I will give you a few tips on how to write proofs and a few practice problems. So, my first tip is to realize that when you're asked to prove a universal statement, if you go about it by providing one or a few examples of elements for which the property in the theorem holds, that does not constitute a proof. You cannot prove a universal statement just by considering one or a few examples, unless, of course, your set of examples covers the whole universe. But that's unusual since typically a universe would be infinite. So just remember, considering examples might help you understand a proof, but proving something for a few examples is not the same as proving it for a universal statement with a for all x. My second tip has to do with drawing pictures. In most cases, a picture does not constitute a proof. So by drawing a picture, maybe you're helping yourself understanding a proof that someone else wrote, or maybe that you're writing. But a picture by itself does not constitute a proof. And the reason for that is the way you draw the picture is very specific. And it's unlikely that the picture you drew cover all the possible cases that are covered by the theorem. Now, there's one situation where a picture may constitute a valid proof, as long as you add a written explanation with the picture, because a picture by itself is typically not enough. However, the point in this third tip is that sometimes a picture, a well-chosen picture, together with a couple of sentences, might be enough to prove a theorem, especially if the theorem says that something is not universally true, meaning it's not true that for all x, p of x. Well, to prove such a theorem, all you need is a counterexample, and you just need one of them. If you can draw this counterexample and explain it with a well-written sentence in English, then that could in itself constitute a proof. But that's a very limited case. It's only for the case of a single counterexample being enough to constitute a proof. My next piece of advice might seem trivial, but it's actually very helpful, trust me, in saving you a lot of points. Of course, you should always double-check your work, and in particular, you should always check your arithmetic and algebraic manipulations. For example, when you divide by a number, especially if it's a variable, make sure that that variable can never take on the value 0, since you're not allowed to divide by 0. Another seemingly obvious piece of advice is to not use fallacies, which are by definition invalid reasoning. Remember the two fallacies we mentioned earlier, namely the fallacy of affirming the conclusion and the fallacy of denying the hypothesis. So now it's time for me to discuss another fallacy we haven't mentioned yet, and that one is called begging the question. Begging the question essentially means making a statement without justifying it, so that your reader, the reader of the proof, is not sure why you're claiming that this statement is true. Remember to always justify every non-obvious statement or proposition in your proofs. Now, a particular example, a particularly wicked example of this fallacy is called circular reasoning. Circular reasoning means that you're making an assumption in your proof, and this assumption is actually the result that you're trying to prove. In other words, you're assuming that something is true somewhere in the middle of your proof, even though the goal of your proof is to prove that this statement is true. Now you might say, that's so obvious that I wouldn't make such a mistake. Well, let me give you an example, very common example. Say you want to prove the following theorem, namely that a times a plus b plus b plus a times b is equal to a plus b squared. Now, how would you prove such a theorem? Well, one way to do it is to start from the two expressions on each side of the equality and to start rewriting them using algebraic manipulations that are valid and completely correct. So you start multiplying out the terms, maybe rearranging the terms or rewriting the terms. And on every line, you perform a step that's very logical and completely correct. Let's assume that all the arithmetic operations here are correct. And you keep doing this until you reach a line where the two sides of the equality are exactly the same. And therefore, you're entitled to prove or to conclude that you proved the theorem, namely that the two expressions are equal. And that concludes the proof. Now, what do you think about this proof? Well, this proof is what we call an informal proof. Remember, we're not justifying every line here. We're not writing a justification next to every line as to why this line logically follows from this one. The reason we don't do that is because it's obvious from the manipulations we're doing and we assume the reader can figure it out. So that's not the problem. This line logically follows from that one. And that one logically follows from that one. And that one also logically follows from that one. Therefore, this proof is just fine. Well, of course it's not. So what is the problem here? This is not a proof. This is complete garbage. Why? Because my question to you is, how do you justify the first line in the proof? Remember, every line would be a true statement. How do you justify this line? Well, you can't assume it's a premise, because this line is the goal of the theorem. It's what you have to prove. So you certainly can't assume that it's true since you're trying to prove it. And by doing this, you're actually committing the fallacy that I was mentioning before, called begging the question or circular reasoning. And this mistake is done very often. So the point is, remember that every line in a proof must be a true proposition that you can justify, or that's obviously true. And let me make that my next piece of advice or tip. Every line in a proof must be a true proposition. What's a true proposition? Well, first of all, it must be a proposition, and that's crux. So let me give you one more counterexample of a similar proof. Let's say someone asks you to prove that a plus b squared is always equal to a squared plus 2 times ab plus b squared. Here is a typical proof or counterexample of a proof that I often see. Someone will start with the left-hand side of the theorem, say a plus b squared, and they will start performing similar arithmetic manipulations or algebraic manipulation that we just saw. Keep going, they don't make any error on any line until they end up with the final result. Now, what is the problem with this? Well, this is not a proof at all. It's as bad or maybe even worse as the previous one. The problem here is that if you call this a proof, then I'm going to tell you, show me that every line in this proof is a true proposition. So, is this a true proposition? Well, of course not. It's not even a proposition. A plus b squared is a number. It's not a true or false statement. In fact, every single line in this proof is not a proposition. If it's not a proposition, it's not a true proposition, so there's no chance of this being any kind of proof. So this is my last piece of advice. Try to review these tips as you progress through the course, and if you avoid all of these mistakes, you have a very good chance of doing well in this course. So to conclude this second lecture on proof techniques, I'm going to leave you with a bunch of practice problems for you to work on at home. The fourth theorem in this lecture and the first practice problem ask you to prove that if n is an odd integer, then 3n is also odd. The fifth theorem that you should work on is that if n is an odd integer, then n squared plus n is even. Here is another practice problem for you to prove. The theorem says if n squared is not divisible by 4, then n must be odd. Here is yet another one. If n is of the form 4k minus 1, where k is any integer, then n squared minus n is not divisible by 4. And finally, the last practice problem for this lecture asks you to prove the following theorem. Every perfect square is either a multiple of 4 or of the form 4k plus 1, where k is again any integer. So as you work on these practice problems, make sure you do your best and then write down your questions. But the three main steps you should always go through for each problem is, first, make sure you understand the statement of the theorem and make sure you analyze it in enough detail to allow you to pick an appropriate proof technique, one that will allow you to complete the proof and that will be elegant and ideally short. The second step, of course, once you've picked a proof technique, is to apply it and to write a correct proof. And the third step, again, is to double check your work, go through every step, make sure you didn't make any arithmetic mistakes or use some fallacies and so on. After you practice with these theorems, I'm confident that you'll be comfortable writing basic proofs. In the rest of the course, we will develop more advanced proof techniques, so make sure you're comfortable with these ones before moving on.